Good morning. It's my first time presenting, but not my first time to India. So thank you for the opportunity. Honeywell thanks you also. The agenda for us today will be, we'll talk a little bit about Honeywell. Honeywell, as you know, is I think not as well known in this Masterbatch space as the additives business, which initially was for AC waxes, but we'll talk a little bit about Honeywell. We'll talk a little bit about how AC waxes are used in the color Masterbatch space. We'll talk a little bit about the wax world, and we'll talk a little bit about engineered plastics, and we'll draw some conclusions, and I'll take some questions and answers. Honeywell is basically about a $40 billion corporation. It has about more than 50% of its sales outside the US. It's basically broken into 4 divisions. We have basically the aerospace division, which is heavily involved in cockpit and landing systems. The home building technologies, which I believe is getting quite a lot of advertising through their filters and whatnot in India. And then they have a whole safety product division. And then the division that the wax additives business is in is basically the performance materials and technology division. This is about a quarter of the overall Honeywell business. It's got basically 3 divisions, the UOP and HPS, which are heavily involved in petrochemical and process automation. And the division that the AC additives business is involved in is basically the advanced materials business. This is basically the one bucket or business unit that Honeywell has all its material businesses in. This basically comprises maybe 4 or 5 different businesses. One of the biggest part of this business is the fluorines. Genetron is the brand name that they use. It's used a lot in refrigeration and cooling systems. They've also come up with a new technology where the gas is used in polyurethane insulation. It's basically the blowing agent, and it's been very successful. Obviously, they have electronics materials that goes into a lot of electronics. They make high purity solvents. And then obviously they have healthcare packaging, which is basically, the product is Aclar. It's a very special fluoropolymer. It's basically a CTFE, and it's got the best oxygen barrier properties, bar none. So it is used quite a lot in medical packaging. Obviously, we also have a Spectra, which is the brand name for Honeywell's fiber and composite. This is an ultra high molecular weight polyethylene that is used a lot in defense for bulletproof vests, helmets, and it's got great strength to weight ratio, and it's a very good product. And then the business that we are in, which is the specialty additives, which is the brand name is AC, which stands for Allied Chemical waxes. This is basically the specialty additives business that I'm a part of. We've been in the additives business now for over 65 years. We produce a large portfolio of different types of waxes with different chemistries, and we'll talk a bit about that as we go on. They're used quite a lot in the plastic space for PVC processing. They are used. Obviously, what we'll talk about today is color Masterbatch, where they play a significant role, and also they're used in other applications like inks and coatings, where they give great mar resistance and surface properties. A newer area for us is the asphalt business, where we've developed over the last few years, where it provides better paving, lower paving temperatures. You can use our additives, and it can help with that. So this is the overall specialty additives portfolio that I'll talk a little bit more about today. Let's sort of switch gears and talk about basically these wax additives. This is basically the wax landscape. As you can see, we break it down into what you call natural waxes and synthetic waxes. Natural waxes have been around for a long time. Oh, sorry. I got ahead of myself there, sorry. So, they've been around for millenniums. But obviously the synthetic waxes, which are made by design, are much more in the recent history. I guess they're a more recent invention. We basically fall under olefin for synthetics. And There's also some other processes, but basically our products come out of the crude oil refining process. Obviously, there are some paraffin wax in that, which is our byproduct of refining. But basically, when you take the crude and you crack it, you basically get our basic building block, which is ethylene. And from this ethylene, we basically make polyethylene wax. And that's where we play today. Obviously, the ethylene can also be used to make polyethylene resin. And that basically is a high molecular weight version of what we make. There's also what we call byproduct wax, which is basically a byproduct of high-density polyethylene resin manufacturing. They make a byproduct, which is also a PE. And then the other way to get to wax is basically TD wax, which is basically they take the resin, they degrade it, and you end up with a TD wax. But we basically play in the polyethylene, I was looking for the pointer. Oh, there. This is us, basically the PE space. This is basically the product line. You can see we basically take ethylene and we make low-density polyethylene. We can also make high-density polyethylene. We do some propylene. And then we do two copolymers where we take the ethylene, react it with vinyl acetate, and we make ethylene vinyl acetate. And then we make acrylic acid, and we make ethylene acrylic acid copolymers. We also do further functionalization where once we do the polymerization, then we can add certain functionality, whether it be maleic anhydride functionality to make an ethylene maleic anhydride polymer. We can oxidize to make an oxidized polyethylene or low density or high density. And then obviously we take the maleation on the polypropylene and make basically maleated polyethylene type waxes. Obviously the EVA we can also oxidize, which is an interesting product, not so much used in the plastic space, but in other coatings it is used. And then obviously the EAA copolymer we take and then we neutralize it either with a calcium or zinc salt. You can basically do that with any type of salt, but for commercial purposes, the calcium, zinc, and sodium are basically the most often used. So as you can see from the last slide, we have many different products, and we basically make many different variations through functionalization. And then, in a sense, the morphology of what comes out at the end can vary quite a lot. But for the purposes of color master batch and plastic compounding, atomization is probably the most preferred form of the product. It falls in around the 200 to 300 micron range. It basically gives good, quick homogenization of the wax when you process it through extrusion equipment. Prills can also be used. They're slightly bigger, but for color master batch applications, they tend to be only able to be used if you're melting the wax first and then possibly adding the pigment into the molten wax. But for most cases, atomization is the preferred product to be used. You can also use micronized waxes, which tend to be used a little bit. Some waxes cannot be easily micronized, so they're used less, but they're also an option. So why use wax in color master batch? Why not just use the resin? I guess the takeaway is that by adding the dispersing wax, you get more out of the pigment, more color strength. So you look on the right there, you can see that it's got no wax, so the color, same amount of pigment. Once you add some PE homopolymer, you get better color strength. This is a good example just to show, why put these additives into the polymer system. Because basically the pigment is usually the most expensive component of the master batch. So if you can basically add value or improve the dispersion, this is basically the result. This is sort of just give you an overview of basically the value chain for the color master batch producer from the dispersing aid standpoint. What does he really look for in the dispersing wax or dispersion aid? Odor and color, obviously, less odor and less color is usually preferred. Viscosity is a very important component, and we'll talk a little bit more about that later, but basically, too low of viscosity in the dispersant doesn't really give you good dispersion. There is sort of a sweet spot that works well. Too high, it doesn't give good wetting and dispersion. Drop point is another important component we'll talk about, and heat stability. Obviously, FPV and color strength and spec count are the preferred method to evaluate the dispersion. And then at the end user's point, the appearance and consistency of the color master batch is obviously paramount, but the properties of the wax can have an important effect on things like prayed out, printability, spinnability, and we'll talk a little bit more about that as we go on. But this sort of gives you an overview of the value chain for the color master batch producer when it comes to thinking about the dispersion wax to use. Let's talk a little bit about wax selection. Obviously, good compatibility with the resin to avoid played out and some issues downstream is very important. If you look at my next slide, you'll see this was basically a color master batch that was made on a twin screw with phthalo blue. 3 different types of waxes were used. There was a letdown done, and then the letdown was pressed into plaques. And as you can see, over time, because of low ends on the ones to the right, you basically get a blooming or whitening effect, which is basically, can be a problem, especially after you make your color master batch, you leave it on the shelf. This blooming effect can materialize, and it's not necessarily good. Heat stability. Basically, to avoid decomposition during the processing and obviously downstream applications, if the wax doesn't have good quality or it's got too many low molecular weight ends, this can lead to processing and end-use application problems. This is an example of how you would measure the heat stability of the wax. You basically do a TGA. You can see in this case, one was a synthetic PE wax, the other is basically a byproduct PE wax. So the thermal stability is much lower, and this obviously can lead to downstream problems, which would not be good in the end application. Excuse me. Polarity. In certain instances, the polarity of the wax can act as a benefit in getting better dispersion and wetting of the pigment. And in other words, it can show improvement in FPV or in color strength development. A couple examples of that would be, here's an example of a green PE master batch that was let down into a film. The one on the left, you can see, has 5% wax. It was let down into a PE film, and you can see that the dispersion and the uniformity was after one pass in the extruder was not that great. Basically, by taking some of the PE and substituting with an oxidized PE at 20% of the overall loading, passing it through the twin screw again, and then doing a letdown, you can see you get improved dispersion and uniformity of the master batch. So this is an example in a PE master batch where polarity actually does benefit the system. Another example, this would be for film, would be in a fiber application where you basically, in formulation 1, you see you've high-loaded red pigment. You've basically got an FPV of about 2.6 after one pass through the extruder. In formulation 2, you can see, again, by partial substitution, about 25% of the PE wax with an oxidized, you can get a lower FPV after one pass through the extruder and meet the specification. So basically, the takeaway here is that, sometimes by wax choice, you can really improve or get the productivity of one pass versus two pass to meet the specification. So again, this is one or two examples of how wax polarity can have a benefit with certain types of pigments. Obviously, in the first case, it was as a green pigment. In the second case, it was basically a red hue pigment. Another, not last but not least, the other important property for wetting and getting good dispersion is the viscosity of the wax. Basically, there's almost like a sweet spot with regard to viscosity or molecular weight, especially with higher-end organic types, where if the viscosity is too low, you really won't get good transfer you get wetting, but you won't get good transfer or shear force to get good dispersion. So there is a sweet spot. It's obviously what I would consider a range of, within a certain range, but if it's too low in the range, dispersion will be poor. And obviously, if it's too high, you don't get good wetting and dispersion also. So there is, for a lot of these waxes, a sweet spot. And then this is just an example of where the viscosity range seems to work well in dispersion. Switching gears, we talked about oxidation and how that polarity can infect and improve color dispersion. Another type of wax, which we talked about earlier, is we basically take the ethylene PE wax and we add some functionality in the form of vinyl acetate. We can add different amounts of vinyl acetate, but for color master batch applications, we find that 13 to 15% vinyl acetate on the wax seems to work well. In other words, with this amount of vinyl acetate, it improves the compatibility of the wax with different resin systems. So not only is it still good in polyolefins, but with resins like PVA or EVA or styrene, you can get better compatibility. So the primary function, again, is to give dispersion of the pigment, but the functionality on the wax basically gives you better compatibility with different resins. This is an example of that. In other words, we have, in this case, a TPU resin with 25% green pigment, or blue pigment, sorry. And we've looked at 3 different waxes at an 8% loading in the master batch, and then we did a letdown of the master batch. And you can see that in this type of resin system, the EVA wax gives you an improved dispersion versus the other types. Here you can see quite good dispersion in this resin system. Switching again, that was EVA. Let's talk a little bit about ethylene acrylic acid copolymers and the neutralized versions of those. So in other words, we make an ethylene acid copolymer, we can also neutralize it. We did a case study on this in PET fiber, where we basically made up some master batches in white and black, as you can see, and in blue and green, with different loadings of wax, 1 to 5%. We basically ran this through a twin screw extruder, and then once we made the master batch, we did a FPV test through a 5 micron screen. And the results here show you is that the EVA wax 540 did a pretty good job in white and black. You can see pretty low FPV here, 0.1 through a 5 micron screen, a little bit higher in the black. And the ionomized version of the 540, which is the Acklin 295, seemed to do a little bit better performance in green and similar in blue. So basically the takeaway from our little case study was that the EVA is pretty good for dispersion in white and black PET, and that the ionomer, which is basically the neutralized version, does a better job in blue and green. And obviously these wax have pretty good heat stability in the PET. So in summary, or not in summary, but so we talked a little bit about oxidized wax, EVA wax, ethylene acrylic wax, and how they work in color master batch. Since this is also a little bit about compounding, these products are also used in engineered plastics for compounding. They obviously give good gloss and uniformity. They open the process window in extrusion, especially in fill systems. And again, they've got good low odor. Some of these ionomers actually can be are used for a little bit of nucleation. And the last one is basically the maleics. We haven't really talked about that chemistry as much, but these are used in that space also. I've put together a few examples of where we've sort of been successful in the marketplace with some of these products. Again, you can see on the left, you basically have the resin system, which is basically nylon, glass reinforced. We see some good basic uniformity of fiber. When you put the wax in there, it gives you good coating of the fiber, good uniform surface. So we have had some success in that area with the EVA wax. Other example we talked about was the third one down was nucleation. They're used in some applications as nucleating agents. The last one is a little different. It's basically a high density in a polycarbonate white that was used for an electrical box system. They used the 307, which is really not compatible, but at very low loading, it does give a very good metal release and injection molding metal release. Switching gears, these are some of the examples of where we have been successful with some of our malleated products. The first one is basically a polycarbonate ABS fill system, where they use the malleated PP, gets good lubrication and good surface at pretty low loading. The other two cases, one is basically polypropylene polyethylene. The 597 is a polypropylene malleated product, and it again gives good improved surface and good lubrication. And obviously, if it's a PE system, a PE malleated product, the 573 would be a better option because it's more compatible. Basically, the remarks section, it mentions that these aren't really replacements for high molecular weight. They basically work in conjunction with the high molecular weight malleated products, but they do have good compatibility and do have good synergy in these types of systems. So again, this is obviously the product range that we sell into this market space. Obviously, the ones that you know are obviously the straight polyethylenes like AC6, 16 are too well known. The oxidized grades like 629, we talked a little bit about how that functionality can work in different, some pigment systems, giving you better dispersion. The EVAs, obviously, for better compatibility with different types of more than polyolefin resins. The acrylics, a little bit about the malleated products, and then obviously the ionomers. So in closing, you know, this space has many requirements. Some of them are low, some of them are high, but I think we have an offering that basically helps in a lot of these applications. We have a broad product range of products and a good value proposition, and obviously we have a technical support here in India and around the world, and we're always here to help. So with that, I'd like to thank you for your time, and if there's any questions.
Hello, my name is Ajit Deshpande. I am from Lifeline Technologies. We are regularly manufacturing color master batches and using your AC6 wax also. My question is, while making the premix, the termination of premix should be made on the time basis or temperature basis of the batch, which will give you better dispersion.
Sorry, did you, huh? I didn't hear the question. Repeat the last question.
We are making premix by using, suppose, polyethylene polymer, powder form, your wax, and the color pigments. We make the premix on the time basis, means time of the premix should be fixed, or the termination of the premix should be made on the temperature basis of the batch temperature, in the high-speed mixer.
So the question was, in the high-speed mixer, should the wax
we are using
time of mixing should be fixed? Is that
or it should be terminated on temperature basis, temperature of the batch.
So, so the question is time fixed or is?
Should be terminated on temperature of the batch in the mixer, high-speed mixer.
Well, typically, my assumption was it's basically once are you fluxing the premix?
Because what we have noticed, if you terminate the batch on the time basis, there is a variation in the shade in the subsequent batches when they are processed on the twin screw extruder.
Right. So basically, I think the answer is that the wax, based on the melt temperature of the wax, and
yes,
it will change with the different melt temperature of the wax. So if the wax temperature slightly changes, meaning you change wax in the mix, it will change the time because the wax temperature is different. I guess that's, are you saying from batch to batch, or if you go from one wax to another wax?
No, batch to batch. Using the same batch, same recipe, there is a variation in the color shade if you mix for the different time.
Right. So
because what is happening when you
yes,
put
the wax is basically softening, you're saying, and once it's are you you know what I mean when you say are you fluxing the premix? Are you softening the wax and getting it dedusted?
Yeah, because what is happening, see for the first batch, time may be 5 minutes for premix, okay?
Right.
Certain temperature is generated due to friction. So suppose for next batch, if I keep the time fixed, in the first batch the temperature is 50 degrees, the second batch it is going above 50 degrees, maybe 55, 57, by keeping the premix time same. The reason is, during the first batch, already frictional heat is generated and that taking the batch
Yes.
temperature to X.
Right,
And if I keep the same time, it is X plus something.
right, right.
And that is the reason why we are getting variation in shade in the subsequent batches.
Yes.
So my question is whether we should terminate on certain 55, 60 or whatever it is on the temperature basis.
Yes. I believe so, but let's talk offline just to, so we can make sure I understand your point.
Okay.
Okay? Thank you.